Okay, hello everyone to our last seminar on interval methods in control engineering before a short summer break. And I'm especially happy to welcome Katja Auer today. Katja is a very good friend of mine and also a long-term collaborator. I think we're collaborating since around 20 years, approximately. And let me give you a brief introduction about Katja's biography. She studied mathematics and computer science at two universities, at the Ulyanov State University in Russia, where she received her diploma in 2001, and at the University of Duisburg-Essen in Germany, receiving her diploma in 2002. Afterwards, she defended her habilitation at the University of Duisburg-Essen in 2014. And right afterwards, in 2015, she has become a full professor of mathematics at the Department of Electrical Engineering at the University of Applied Sciences in Wismar. And this is also where she's currently working. And we are looking forward to your presentation on the uses of methods with result verification for dealing with uncertainty during MIMO modeling and simulation processes. Okay, the floor is yours, Katja.
Thank you, Andreas, for this kind introduction. Hello, everybody, and welcome to my talk. So I'm happy that I have the opportunity to talk to you today and that you are listening. So this is a joint work with my colleague from Wismar, Andreas Ahrens. So what I'm going to talk about today. So I think I don't need to explain to this audience about really about this about result verification, but just maybe a few words. So verification answers the question of where we are building the product in the right way. And there are different kinds of verification, for example, formal verification, code verification. Formal verification, for example, model checking is used to prove that some certain systems, for example, chips, computer chips are working properly. So with the help of the code verification, we usually want to see if a program, the code of a program is written in a correct way. And using result verification, for example, with the help of internal arithmetic, we are doing the following. Well, I'm sorry, it's quite loud noise now coming from the window. I close the window now so that we don't hear the noise. I'm sorry, it just started. Okay, so result verification. Here we want to prove mathematically that the results we obtain on a computer using floating point arithmetic is actually correct. Yes, and this is done using some fixed point theorems and combinations with set-based arithmetic. The advantages here is that we can account for rounding or conversion errors that we are doing on a computer, but we can also propagate epistemic uncertainty through the systems in a forward way using this kind of methods. So a major disadvantage here is the possibility of too pessimistic results, that is of overestimation. It can happen that at the end of the forward simulation we get bounds for our exact result that we cannot meaningfully employ, for example, from minus to plus infinity or some such. So, and the approaches that we all know about here in this context in the seminar, interval affine Taylor models and so on based methods. So, methods with result verification were applied in many different contexts, beginning from the computer-assisted proofs. For example, in 2002, Warwick Tucker proved this 13th Smail's problem. So, but the major area here, application area, is I think engineering. So we have here, for example, applications in robotics, chemical engineering, particle accelerators, control theory, and many more. Also in other fields, result verification is applied, for example, in computer graphics, finance decision making, imprecise probability. And now I'm going to talk about how we can combine result verification, or how can we use the approaches that we know from the result verification in the area of wireless communications. So, what are we going to focus on? So we are going to talk about the so-called multiple input, multiple output systems with the help of multiple input. Well, this technique helps to improve channel capacity or integrity without increasing the channel bandwidth or the transmit power. So the method is to put or let's say to transmit multiple data streams on the same frequency band at the same time. So and or let's say we have to look out for spatial separation. That means those multiple antennas on the receive and transmit side need to be separated spatially. They need to be placed at different locations. So, and if those locations are too close to each other, then the so-called correlation effect may happen. That means that the transmit to receive path might become too similar, impairing the transmission. So this is a point that we will also take a closer look on during this talk. We will compare the things for correlated and non-correlated channels, but how we are going to compare them. Well, the channel capacity, one possibility to characterize the channel capacity is the information theoretical limit on the so-called bit error ratio, BER. And this characteristic describes the number of bits per second that can be transmitted through a physical channel error-free. So let's take a look at the general modeling and simulation of a MIMO digital channel. So we are going to focus on this criterion of BER. And what steps are necessary to model and simulate such a channel? So first, the system configuration needs to be decided on. So we specify the number of transmit and receive antennas, some other hardware maybe. And this is the stage where we need to take care or look out for the correlation effect. So here we can have high or low correlation effect. So after the system is configured, the next step is to estimate the channel. So, and well, usually the so-called linear stochastic model is used, where we have this representation, which is also shown here, where H is a channel matrix containing well, some fading coefficients, yes. And if we consider this entrance in the matrix H or entry in the matrix H, then we will have well, it describes the fading from the JF of the JF receive antenna and the ETH from the ETH transmit antenna. So, and usually this channel matrix is a complex matrix depending on the number of receive and transmit antennas, and it is modeled or estimated using the normal least squares optimization here via so-called pilot sequences. That is, known sequences are transmitted through the system, yes, and then we take a look at what we receive and try to optimize the transmission depending on those results. So this stage is not in the focus of our talk today. So, okay, after we've estimated this channel matrix, the next stage is a so-called interference suppression. So we see that if we consider this model, so this is the transmitted signal, this is the received signal. So, and here are the fading coefficients. So we see that, well, interference, depending on the matrix H, we might have interference here in the signals. This is the noise, yes? So, and the purpose of this stage in the process is to suppress this interference. Yes, and for example, this can be done using the so-called singular value decomposition. And if we use this, then we obtain a number of independent, weighted, single input, single output links. That result from this diagonal matrix sigma. Sigma contains then the square roots of positive eigenvalues of this matrix H, yes? And using this singular value decomposition, we can decompose this matrix H in this way so that we have unary matrices U and V. And then if we pre-process the input or transmit signal using the matrix V and post-process this signal using the conjugate transpose of the matrix U, then, well, this kind of model appears where we also post-process the original noise signal using this matrix, and we obtain here well, a number of those independent weighted links, which are ideally, or in the ideal case, non-interfering. Yeah, so this is something we would like to do, or which is done using the singular value decomposition. After that, we go to the resources allocation stage. So if we use singular value decomposition, then we need to allocate power, additional power to some of those independent weighted links. Also, bit allocation can be done to optimize the system. And for that, we can use, for example, the Lagrange multipliers optimization. So, and of course, we can see, we can compare here results without power allocation, results with power allocation using this criterion of BER. So, at the stage of the resources allocation, we have what describes the stage is the number of activated layers and the transmit power per layer and the constellation size L. Each stage might be affected by uncertainty in numerical errors, and let me explain what we have, what kinds of uncertainty we can have in the system. Well, MIMO systems can achieve high capacity gains, but this is only supposing that we have perfect channel state information. And of course, we don't have perfect channel state information. This imperfect knowledge might be due to, at the channel estimation stage, due to channel estimation error at the receiver or limited feedback capability of the MIMO link. So at the stages of interference, suppression, and resources allocation, we might have uncertainty in the singular values of the matrix H. We can have uncertain noise variance at the receiver side. And of course, those things, for example, described at this stage were, of course, already treated. Some of these aspects were already treated in the literature, but the techniques that they're using are the traditional uncertainty quantification techniques. That means that they just use the probability theory to deal with that. And well, what we want or what we would like to try to do is to combine to use a combined treatment for such problems, also with the help of verified techniques, also mathematical notions from verification in combination with the usual and traditional uncertainty quantification techniques. Now let me talk a little bit more about those correlated and correlated channel realizations. Again, depending on how the antennas are placed, we can have good or poor scattering conditions for the antennas. What we notice from the previous slide here is that those weights are singular values, and of course they are not equal usually. And if we additionally have the proximity, then this problem might get stronger. A good indicator or a simple indicator for that is a ratio of the smallest singular to the largest singular value. And here's an illustration. We consider a MIMO channel with 4 receiving, 4 transmitting antennas. For the uncorrelated and correlated case, so this is a channel with 5,000 realizations for the uncorrelated and correlated case. And then we compute those ratio, then we see that in the uncorrelated case, so the mean value is approximately here, so we are more likely to get the values of the coefficient above 0.1. And if we have the correlated, the correlated case now, the mean value is somewhere here, let's say for the frequency, so we are more likely to get the values of 0.05, well, which is quite small. So now we would take a look at the guaranteed Br minimization. So how can we do this in a guaranteed way? Yeah, so this information theoretical bound on the BER can be expressed using this formula, where we have the complementary error function here, depending on the singular values, transmit power, then of course those variance, noise variance at the receiver, but also on the constellation size, number of active layers. So what we suppose or assume in this talk is that this coefficient is constant. That is that the channel has a constant throughput. Yeah. So for example, 8 or something like that. Yeah. So the throughput is constant. We don't want to optimize with respect to the throughput of the channel. So what we want to do is to minimize this BER with respect to uncertain singular values and the uncertain noise. Variance, or let's say uncertain noise standard deviation in this case. Yes. So, and the fact is that we don't need to do this in using integral arithmetics on a computer. What we can do is we see that this function that we have here is monotonically decreasing. Yeah. Then using the normal rules of integral arithmetic, we can compute the upper bound for the BR, which we then minimize. Yes. So, and the upper bound is, of course, looks the same as here, but we use, of course, now the lower bound for the singular value and the upper bound for the noise. Yeah, so in order, well, this is just using normal rules of integral arithmetic to obtain the upper bound, because it is possible in this case to do this in a piece of paper, because the function is quite simple and monotonic. So we can now minimize with respect to different factors. Yeah, so for example, we can minimize with respect to this. This is the power per layer. So this is called power allocation, or we can optimize with respect to the number of active layers and to the constellation size. This is called bit allocation. So this is obviously, well, we don't want to optimize with respect to that, but well, with respect to other parameters. So the noise variance is, of course, nothing that we can optimize against, because this is somehow a given a parameter of the system. Yes, and we can optimize with respect to all other variables that appear inside the BR. So, if we want to do power allocation, then the normal Lagrange multipliers optimization in combination with software with result verification can help already. Yes, and in the case of bit allocation, we have a nonlinear mixed integer programming program. Yeah, so that those are natural numbers such as, well, usually powers of 2. So, and that is, we have, well, a mixed integer programming problem. Yes, again, we can use software with result verification and power allocation to, well, try out what kind of constellations are optimal for our system. Well, let's start with power allocation. So what is the problem formulation? The idea here is to assign more power to the layers with more weights. Here we assume that those variables are fixed. So normally we have the equally distributed power. So, and we modify now this power using those coefficients pi squared, so that the constraint must be fulfilled that the sum of all powers per layer is again equal to the power. So we can well, if we use instead of that, again, the definition PS over L, then this constraint is simplified to the PL squared is equal to L for L small from 1 to LB. Yes, so, yes, and so this is a constraint shown here, and using the Lagrange multipliers method, then we can use, we obtain those goal functions, function that we need to optimize. So what options do we have here? The first possibility is to mix analytical and numerical techniques and obtain a system for computing the stationary points on a piece of paper, yes? So because the goal function that I've shown you on the previous page is not so very complicated that we need to obtain the derivatives here in any other, well, for example, using automatic differentiation or some such, so we can obtain this on a piece of paper and they always look like that. Yeah, so, what we know is that, well, according to each of those optimizing coefficients pi sub L, yeah, so those are the partial derivatives, and the derivative with respect to the Lagrange coefficient mu is just a constraint, yeah, so this is the system that we need to solve. And here we have some coefficients that do not depend on the pi. For example, this KL and CL, they are both positive just from the form of those coefficients. And now we can solve this system using software with result verification, for example, a solver which is available in CXCC. Yes, what we can additionally show here is that the Hessian is built in such a way that the stationary point that we obtained here as a solution is actually a local minimum. Yes, and of course, the second possibility is to use directly global optimization directly again, for example, in CXC. So, of course, what we found out is the second possibility is more affected by overestimation. So, if here is an example, what we get, what kind of overestimation we can get. Again, we consider a MIMO link with 4 antennas and 4 active layers. So the throughput is 8 and the power is 1 watt. And we consider just one data set here with those single values. This is a strongly correlated system with this correlation coefficient. So, and the results for the optimal values of those power allocation parameters at the given signal to noise ratio of 10 dB are for the possibility to actually of the width of, well, the maximum width would be, well, in a, let's say, in the area of 10 to the power of -2, so something like that. Yeah. For the possibility 2, that means if we use global optimization directly, of course, well, not of course, it's not so very obvious, but actually, if we solve the system of non-linear equations directly, well, then we see that we can get a much tighter intervals for our coefficients. Yeah, for our coefficients in this case. All right, so now let's take a look at the bordered Hessian. So because we have a constraint, we have just one constraint. Yeah, so we have a border of just one column and one row, this Hessian, and the second derivatives with respect to each of those coefficients P sub L small, are also actually simple because we only have a non-zero values at the diagonal here and all other values are zeros. Yeah, and if you take a look at those derivatives that we have here, we see from the previous slide, not from this one, that well, this is positive, yes? So this is also positive because of the problem we have. This is minus sign, it should be equal to 0. That is, we know that mu should also be positive, yeah? And if we take a look now at the Hessian, we see that all the things that appear inside the sum are positive, yes? So that is all of those values that are given here are positive. And now, if you want to compute the so-called principal minors of this bordered Hessian, then it can be shown that they all have this form where well, this coefficient is positive, and well, this is something which is coming from the border. This would be A1, this would be AL. So, and those are our D's here. So we know all of them are positive, so, and we have a sum of positive coefficients, and we have here minus, that does all of those principal minors will be less than 0, and that shows us that we have a local minimum and the values of pi that we will compute. Yeah. So, and if we are able to compute a unique solution, then we will have a globality and know that it is truly the minimum of our PER. So, here's a special case of power allocation. A case that appears quite often in practice is when we have two active layers and the constellation size chosen in such a way that those two values are equal. In this case, we will obtain, or in the usual way, the system of equations that we need to solve, and this can be reduced just to one single equation for our pi1. Well, unfortunately, even this equation cannot be solved analytically, so we need to solve this equation using some numerical methods. But what we can see from this is that the common practice that is often used in MIMO system for choosing the coefficients pi1 and pi2 in such a way that they are equal to the ratio of lambda 2 lambda 1 is actually not optimal, because this does not solve the equation that we derive. Yeah, so this is not a good practice, and we will not obtain the optimal BR in this way. So here's an example for the special case. Yeah, so actually the solution is the intersection of a hyperbola and an exponential function with the negative argument, and we are looking for a solution. Well, of course, that should satisfy our constraint, that is a solution between 0 and 2. And here in this example, we see that the solution is somewhere here. Yeah, so it can be obtained in this way. Okay, what about bit allocation? As in the case of bit allocation, we optimize with the help, with respect to those constellation sizes. So we see from the formula that those constellation sizes influence the overall bit error ratio, but also the number of active layers, yes, given the constant throughput that we have here, the throughput T. So what possibilities do we have for a constant throughput? Yes, so for a constant throughput T equal to 8, we will have those possibilities for constellations. Yes, so those are not all possibilities, but some of them. Yes, so for example, yeah, and here's how the corresponding BR would look like for the case of lower correlation. So we see that the chosen number of active layers give us better or worse BR. Yeah. So, and well, if we have a throughput which is relatively small, then we can just use a brute force approach to find the optimal constellation form. Well, what is better, this or this? So we do not know. And well, we can find out by brute force if the throughputs considered throughput or given throughputs are small, and if we don't have an awfully big number of antennas. So, and this is what we've done for the example that I've explained about earlier for this 4x4 MIMO systems. Well, we've considered also frequency selective systems, but I show here a simple example of a frequency flat systems with 4 transmitting and 4 receiving antennas, constant throughput of 8 bit per second per hertz, and again the same example of the transmit power of 1 watt. Again, we consider 2 data sets. We have 5,000 channel realization each for the correlated and the uncorrelated case. Again, we see here the amplitudes or the singular values for the uncorrelated, and for the correlated case, we see that in the correlated case, they are, let's say, much further from each other. So, and we show the results for this constant signal to noise ratio of 10 dB again. So again, we consider first power allocation for 4 active layers. Well, there we can choose this constellation sizes. We see that using the methods that I described earlier, verified techniques, we can reduce BR and obtain a pretty tight intervals in each case, and we can reduce the BR for each constellation of singular values for correlated or uncorrelated data set. What about bit allocation? So since the lambdas are given in a decreasing order, then we also only need to consider constellations in a decreasing order. And that's, from this point of view, those are all the cases that we can have in our system. So with the corresponding 1 active layer, 2 active layers, 3 active layers, and 4 active layers, 14 cases. And we found out that the case of 2 active layers is the best for both correlated and uncorrelated case. Those are the BRs for those 5,000 channel realization from the lowest possible BR to the highest possible BR. So we see, of course, that well, here's the optimized BR. Yes, so using power allocation, and this is without power allocation. Yeah, so we see this BR is of course optimized, but we also see that, for example, in this case, which is good for the correlated case, while in the uncorrelated case, this can still be improved a little bit if we use this case with 3 active layers and this kind of constellations. So what we learned from this example is that all 4 layers should never be activated at the same time. That is, examples that I've shown you earlier using 4 active layers, they were not the optimal configurations for the MIMO system from the point of view of those quality criteria of BR. And those 2 cases are then likely to be the optimal configurations for our MIMO system that we've considered. Okay, let me, at the end of my talk, explain what we can still do and what is our future work in this area. What can be done to optimize, what else can be done to optimize the MIMO system? So, and here again, we take a look at the interference suppression stage. So, you remember we have this linear, where is my pen? I don't know. This linear stochastic system, which is characterized by the received, the transmitted signal, and so on and so forth. And so what we've done until now is to is to use the SVD, which gives us this metric sigma having the eigenvalues, the square roots of eigenvalues on the diagonal. So we will obtain a number of independent single input, single output links with unequal weights corresponding to the singular values. So if you do this like that, then we need to equalize somehow here. Now this is the reason why we use the power allocation and bit allocation, this resources allocation stage. Yeah. So to achieve a good BER, we need to optimize further. So another possibility which has been proposed a while ago is to solve the optimization problem that we have for the capacity. Well, not the exact problem, maybe this optimization problem, but well, a similar problem, an approximate solution. Yes, an approximate solution is given by the so-called geometric mean decomposition. So we decompose now not in a number of unequilibrated subchannels, but into a number of identical subchannels. Yes. So we have those identical subchannels here, and this is given by the geometric mean of the singular values of the channel matrix H. So this can be shown to, well, approximately or to be asymptotically optimal, but for high signal-to-noise ratio with respect to both the channel throughput and the BER. So, and this solution supposedly have no trade-off between the capacity of the channel and the BER. Also here we need to optimize somehow with respect to the number of active channels. So, but again, this is a solution for high signal to noise ratios. So will it work for, let's say, normal signal to noise ratio? So this is something we want to explore in our future work. And this is something that we work on now at the moment. So what are the results? The problem that I've described can be solved by a mixed analytical numerical technique. This numerical technique can happen using result verification, so it can be done. What we've learned about here from our experiments is that at least the weakest layer in the MIMO system should be switched off. For correlated systems, we see that the resource allocation plays an especially important role, and the best performance, well, in general, we can say that the best performance is achieved for 2 active layers in our example. So our future work will incorporate the use of GMD instead of SVD for obtaining equal weights. Does the performance really improve for normal signal to noise ratios? And well, of course, we want to analyze our system also with respect to the influence of noise. So not only just for 10 dB, but also for other noise variances. Thank you very much for your attention. Thanks for listening. And now I'm ready to answer questions.
Yes, and many thanks, Katja, for your very interesting presentation. And yes, definitely there will be some questions, I think, in the audience. Is there anyone who wants to start?
Maybe.
Yes, Luc?
Yes, so thank you for this talk. So if I understand in your MIMO, MIMO, I don't know how you have to optimize some criterion. So here it is a BER criterion, and you have some uncertainties. But what I don't understand is that if you have uncertainty, you have a set of global minimum and a set of global minimizers. So you use interval. So which one do you search for? All of them or only for one?
Well, in this case, we can see that, yes, you know, the first thing is that we do not optimize in the interval sense, yes, so we optimize just the upper bound only, yeah. So the upper bound depends on the lower bound for lambda and the upper bound for the noise.
But you optimize the upper bound for what? Which
for the singular value.
okay,
the upper bound for the BR.
Okay, so it's some kind of worst case, yes?
Yes, it's worst case, yes, that's
okay,
right.
okay, that's okay, I was not sure of this.
It's worst case, yeah.
It's a worst case. Because I think it would be also maybe interesting to find all possible, the set of all possible global minimizers, for instance, but it's not what you are interested with. It's a worst case that is interesting.
Yes, it's worst case. Yes.
Okay.
Yes,
okay.
Yes.
That's I wanted to know what.
Well, it's an interesting idea. I just don't. At the moment, I can't relate finding the set of all global optimizers to the problem of BR, to equality criteria. Of course, usually they are interested in the worst case. What best performance can we achieve in the worst case?
Yeah, okay, I understand this because I was not sure, but I think indeed that to find all feasible global minimizers would be an interesting problem. And it could be none, probably, I think. Okay, and I have another question. So all is non-convex, of course.
Yeah.
These materials are non-convex. There is several local minimizers, probably. Probably, okay. And my other question is that I used a long time ago C-axis C, you know, C-axis C, and I wanted to know here, I don't know, the evolution of this tool, this toolbox. So now, a long time ago, it was only related to interval computation. You were also able to, it was made by Kulisch and the team of Karlsruhe. I know something, and I wanted to know how you use it here. You have only to solve your global minimization problem, or?
Well, you can use it to solve this global minimization problem. Yes, you can use it, but this possibility too. It's not working very well, yeah, because well, if we just take an example, then we see that by using the global optimization directly, we will obtain a much worse enclosures. Well, enclosures that are not good, yeah. So, and then you need to restrict the search space. So you need to know approximately where your minimizers are going to be, and so on and so forth. That's why we don't use this option, because it's bad, yeah. So what we can do is to use this mixed technique, yeah. So you obtain a system of nonlinear algebraic equations for your stationary points on a piece of paper, because it's just a simple system that you have. The function, the goal function, is not very complex, yeah. So you can compute the derivative on a piece of paper. It looks like that. So, and then you have this system and can solve it using any verified techniques for solving nonlinear equations. Yes, and there are different packages for that. For example, inside the CXCC again, or you can use anything else. Yes. So, and well, I've used CXCC because I have it here, but I could have used anything.
Okay.
And if you transform this problem like that, then you can show that the solution that you are getting, if you are getting from your tool a unique solution, then this unique solution will give you the global minimum. Yes. So because it can be shown using those bordered Hessian approach. Yes. So you will have a local minimum. This could be shown by bordered Hessian. And if the solution that you obtain from this system is unique, then you have a global minimum.
Okay. Okay. Thank you.
Thank you.
Okay. Do we have any further questions? Okay. Maybe let me ask a question, Katja. If we directly have a look at this slide here, that's, I think, a very classical statement of here's a nonlinear least squares optimization problem, including some nonlinear equality constraints. Just reformulated in this Lagrange multiplier sense. Can you, let's say, give some kind of recommendation when you're using, for example, this approach for general parameter identification, whether always this semi-numerical or semi-analytical approach is better than doing it directly numerically, or is this just a lucky result in your scenario that you have here?
Well, that's a good question. Well, I suppose that usually, well, you cannot prove this, of course, yes, or I cannot prove this at the moment, but inside a global optimizer tool, yeah, so you will have to compute, well, something which resembles the system, yes, but how you compute this? You compute this by using some, I don't know, some automatic differentiation techniques and so on and so forth, and maybe you don't compute, you only compute enclosures of that, yes. So this usually would be worse than producing the derivative. Well, you can say it will be worse, but it depends on how well you are computing the derivative. So this is the point, yes? So if you compute this derivative, for example, like my colleagues did, they computed, for example, something like this derivative using symbolic differentiation, yes? And they obtained such a long code, having so many common sub-expressions that if you evaluate them using even in floating point arithmetic that did not behave stable in a stable way, yeah. So, and that's why, well, at least in this case, it is simpler, or let's say easier for a human to obtain the derivative than it is for a tool, yeah. And that's why I think that's why we are obtaining better results in this case, yes. And usually, I think it is easier to solve a system of nonlinear equations than to solve a global optimization problem. So this is my feeling, yeah, so it is easier. Well, maybe not for each example, you can construct probably some example, but in general, if we just, well, let's say the mean value, yes, so the mean value would be so that it is easier to solve nonlinear system of equation than to prove. Yes, well, you need to do this in a verified way to prove that you have a local minimum. That's why my answer would be probably if you are able to use this mixed technique, yes, so if it is possible to obtain a derivative or anything, any other proof analytically, then probably it would be better to do so than to use a global general purpose tool. So this is my feeling.
Yeah. Yes, okay. And the other question that is, I think it's also quite well known that the optimal Lagrange multiplier that you're computing in such techniques gives some kind of robustness measures of the optimal solution. Is this something that could be exploited here reasonably?
Oh, robustness.
Yes, because you have this mu as the Lagrange multiplier, you
Yeah.
directly get it also from solving your nonlinear set of equations.
Yes.
And the Lagrange multiplier is the sensitivity, the partial derivative of the cost function on the constraint that you have on the right-hand side.
Yes, yes, yes. Mm.
This could
Yeah.
maybe also be interesting to judge somehow your sensitivity at the end.
Sensitivity, maybe, yes, yes. This might be so, but I didn't think about this until now. Actually, thanks for the tip, for the hint. I'm not sure how we can use this directly. So aside from the sensitivity measure, but I need to think about sensitivity of what with respect to what, yeah?
Of what is clear, it's the sensitivity of this BER, of your cost function, with respect to your decision variables at the optimum. This is the value of the Lagrange multiplier.
Yeah, this is the value of the Lagrange multiplier of this cost function with respect to the, for
all your decision
example,
variables.
P, yeah. So we get the value, but in which area the sensitivity should be in order to produce a robust solution?
Okay, that means your question at the end is how to interpret the absolute value that you have at the end.
So this is something, so I can directly see if I get the correct solution by using the constraint, but how to use mu in this context, how to interpret it, so I don't see this directly. So
yes, maybe it's an option if you have similar solution candidates like you had in your table at the end, to make a decision which one, if they are very similar, the cost function values, which one is the better one to choose.
Yeah, this would be, well, until now we didn't have the problem of finding multiple global minimizers. Yes. So, but of course, if we'll encounter this, then maybe this would be a good strategy to choose among them. Yeah.
Yes, and I have one further question. I think it was the slide 18. Where you have this input-output relations between, here's this box on the left-hand side, where you have this input-output relation between the transmitter and the receiver. Because that's always a linear expression that you have. If your transfer matrix, the matrix H, is perfectly known, and if the transmitted signal and also the noise are Gaussian distributed, definitely also the result, the received signal, is Gaussian distributed. Is this something that you can, let's say, exploit during your optimization?
Well, this is something they exploit actually in this BR thing, yeah? So this is something that
okay, this is where this the error function here comes from.
Yeah.
Okay, okay.
Yes, they do this, of course, yeah.
Okay, then it's clear for me. Okay, thanks. Okay, do we have any further question in the audience? I do not think so. Then again, many thanks, Katja, for the presentation, also for your patience to answer all the questions that we had.
For asking.
Yeah, and many thanks also to the audience that you just joined our seminar through this complete second year now of our seminar series. And yes, it will be our great pleasure to restart the seminar at the end of September this year with a new series. And we already have a list of, I think, 5 or 6 tentative presentations that we'll have. And you'll get the information very soon as the first talk after the restart has been scheduled.